In the preceding section, we saw that Hilbert was able to make Euclidean geometry rigorous by expanding Euclid's axiom set and by being meticulous in the logical development of the theorems. The price that Hilbert paid for the added rigor was an axiom set that was considerably larger than Euclid's, and the need to provide rather difficult proofs for a number of obvious results, most notably in the area of betweenness. During Hilbert's lifetime, a number of other geometers were also interested in this area of research, but Hilbert's work has survived as the effort that most nearly conformed to Euclid's approach. An American mathematician, G.D. Birkhoff, provided a noteworthy exposition of Euclidean geometry in 1932. Since Birkhoff's work, like Hilbert's, he was constructed so as to be consistent with the work of Euclid, it provided no new result in terms of its theorem. Rather, its significance lies in the radical different set of axioms he chose to use in the development of the geometry. Birkhoff's axiom set is much smaller than Hilbert, and even smaller in number than Euclid's. Birkhoff took as primitives the terms point, line, distance, and angle, and his four postulates are follows. So, in Birkhoff model for Euclidean geometry, here are the four undefined terms. First is the point. We know naman kung ano yung meaning ng point. The second one is the line, or it defined as a set of points. The third one is the distance between any 2 points. A and B is a non-negative real number distance AB such that distance AB is equal to distance BA. Also, kahit pagbalik-balik ta rin yung dalawa, mag-equal, they are similar to each other. The fourth one is the angle. An angle is formed by three ordered points A, O, B. A is not equal to O, B is not equal to angle AOB such that measure angle AB is a real number modular 2 pi. He is basically postulating that there is an angle measure and a distance measure in existence basically. Definitions. The first one is between. If A, B, and C are distinct points, we say that B is between point A and C such that A minus B minus C if and only if distance AB plus distance BC is equal to distance AC. He talks about a line segment point A and C together with all point B between A and C from the line segment AC. Notice the notation for the line segment AC with the bar over it. A half-line endpoint. The half-line M prime with endpoint O is defined by points O and A in the line M, where A is not equal to O as the set of all points A prime of M such that O is not between A and A prime. So he is able to use betweenness to get to that. The fourth one is the parallel. If two distinct lines have no point in common, then they are parallel. A line is always regarded as being parallel to itself. A straight angle. A right angle when perpendicular to half-line M and through O are said to form a straight angle if the measure MON is equal to pi. Two half-lines M and N through O said to form a right angle if the measure of MON is equal to positive negative pi over 2, in which case we say that M is perpendicular to N. similar congruent. Any two geometric figures are similar if there exists a one-to-one correspondence between the point of the two figures such that all corresponding distances are in proportion and corresponding angles have equal measure, except perhaps for their sign. Any two geometric figures are congruent if they are similar with a constant of proportionality k is equal to n. Now we're going to discuss his four postulates that we notice these all depend on really knowing what the properties of the real numbers are. So the first postulate is the postulate of line measure. Defines the point AB and so on of any line can be put into one-to-one correspondence with the real numbers x so that the xb minus xa is equal to the distance AB for all point A and B. Postulate number 2 is the point line postulate. It says here that one and only one line L contain any two distinct points P and Q. So this postulate is the same with Hilbert postulate. The third postulate is the postulate of angle measure. The half line or rays LM and so on through any point O can be put into one-to-one correspondence with the real numbers A modular to pi, so that if A and B are points other than O of L and M, respectively, the difference of A of M minus A of L all over 2 modular 2 pi of the numbers associated with the lines L and M is M angle AOB. Now we're going to the last postulate, or the postulate number 4, postulate of similarities. If in two triangle ABC and triangle A prime, B prime, C prime, and for some constant of k is greater than O, the distance from A prime to B prime is equal to k times the distance from A to B. The distance from A prime to C prime is equal to k times the distance of AC. The measure angle of B prime, A prime, C prime is equal to the measure of positive negative angle BAC. Then also the distance of B prime, C prime is equal to the k times the distance of BC. M angle C prime, B prime, and A prime is equal to the M positive negative angle CBA. Then the last is M angle A prime, C prime, and B prime is equal to positive negative M angle ACB.